to record this time. So any questions first?
How are you?
I'm all right, thank you. I'm ready for the weekend.
Do you actually have a cat? Like, you always say, cat walked over your keyboard, but I'm just asking, do you have a cat?
Not at the moment.
Not at the moment, okay.
But most of my life I've had a cat or two.
Cats are great.
They are, aren't they? So ODP 201, I think everybody nailed that one, but there's an example of how you could code that up. So basically your function sum, I guess this was a main program for 201. So there's what you were writing, and I already showed you that the first day. So that's not terribly interesting. Let's look at 202. So 202, initialization of the linked list. So typedef struct node, I called it an uppercase node, and it's just the usual structure we're going to be working with through all of this: a data piece, a next piece, and a valid piece, all integers. And then initialize index element 0. We know now this is our sentinel node, so set the data to 42 next to -1, which means no next node, and valid is equal to 1. And then just a straight for loop, 1 through and including 99, set the data next and valid pieces accordingly. And that should assess 100%. So yesterday's ODP, retrieving the first node that's valid, same setup for a struct node. Yeah?
Why did it matter for the order? So it had to be in specific order, data next and valid.
It matters for the order because when you compile your code and you link it and you've got your executable, which is a bunch of 1s and 0s, it doesn't know about this source code. So this is a good thing to discuss. So integer data, and then next, and then valid. Actually, let's do this in GDB, because I'm going to open up a GDB quiz in a few days also. So I'm compiling with a -G flag so I can use GDB. I'm calling the output haha so I don't accidentally overwrite my main. And I'll GDB haha. So I can list. And my main program is going to initialize a bunch of stuff inside my structure. I don't really care about that. So D is a structure, right? It's got 100 elements of these struct nodes, data next valid. Let's just look at the first element, D bracket 0, and let's print out its address. And it's this big long thing that ends with 0E90. And that's where element 0 of our array is stored. So I'm just recording this down here on paper. So let's print the address of D bracket 0 dot next. And that's located at E094. And let's print the address of D bracket 0 dot data. And that's at E090. And can you guess where valid is going to be stored? 98, perfect. You didn't actually guess, did you? So this is what our memory map looks like. The first element of the array is a struct node. It's got 3 integer pieces called data, next, and valid. Data is stored at 90, next at 94, and valid at 98. Why are they in that order? Because that's the order that we declared them in when we wrote our C program, data, next, valid. Now, if your function defines a struct node to be valid, next, data, then in your code, this first location is going to be, say, valid, and this will be next, and this will be data. And anywhere in your code where you said, show me the data piece of this struct node, it's going to say, okay, take the address where the node begins and add 8. That gets me to the data piece. But in my main program, which wrote data, next, valid, if I go to the address of the struct node and I add 8, I'm reading the valid piece. So there's nothing inherently in the memory of the computer that maps this piece of data to that piece of data. It's all positional. And the position is determined by the order in which you specified these in the structure.
So as long as you stay consistent.
As long as you stay consistent, right? The problem is that I'm giving you the main program, and in my main program, that was the order I used. But if you're writing your own program and you're doing everything totally yourself, you could put these in any order that you want. You could make the structure look however you choose, and it should work fine. So GDB can help you with this stuff, and particularly when we get to PA2 and further, you're going to want to use GDB to do things like figure out where things are located in memory. And you can print variables in the usual way, but you can also find out where things are stored by putting an ampersand in front. And you want to get in the habit of making yourself memory maps, right, on a piece of paper. Write down consecutive locations. What are those locations being used for? And if we want to know what's stored at location E09C, right, we can use the examine instruction. We can say examine location 90, 94, 98, 9C, A0, and so on. We can look at the contents of memory. And we can examine things in decimal if we prefer by saying /d, and there's lots of options on the X command. So there's a solution for ODP 203, right? Basically loop through from 0 through 100. You need to begin at 0, and I'm looping while I is less than 100. So it will do 99, it will not do 100. And if your array is defined to hold 100 things, the first index is 0, the last index is 99. Right? It's always one less.
So the reason that we're designing the linked list in the first place is to bring the search function down from n operations to log n operations?
Ultimately.
So if you have to search through every piece of information to find an empty node, doesn't that bring it back up to an n problem?
Yes, it does, because this is not an efficient implementation of a linked list. But in PA2, this get node will be replaced by a system function called malloc. And malloc has efficient ways of finding basically a free node. It uses something called a heap.
So if we doing a PA2, it's a dynamic array of linked list.
If we do PA2, it's not going to be an array at all, but it's going to be dynamic memory. And we're going to use malloc when we want to create a new node. We're going to use free when we want to release a node. And then we don't have to worry about the valid flag. We're just going to have nodes with two pieces, a data piece and a next piece. And the next piece, instead of being an index and array, will actually be a memory location of the next node.
So we need to use a malloc and free, right?
Mm-hmm. Right. And we're going to go through all of that in careful detail.
I had a question about a compiler error I was doing yesterday.
Okay.
So I noticed on your program you had just the structure defined. You didn't put a name, but you said what variables were in it in order.
Right.
You had the comment, and then you had int main.
Mm-hmm.
And I was getting this error where if I did it that way, which is how I got my first program to work, it kept saying like expected token, but if it was void main, or if it was a void function, I wouldn't get that unexpected token or identifier.
That's
so it
weird.
wouldn't let me compile without naming the structure if the function was an integer. But if it was void, it was fine with it.
So,
I get that same error too.
can you show me later?
Yeah.
Okay. If you can show me or shoot it to me in an email.
It's literally like, I even was so confused with the error that I just commented everything out, and I basically wrote a function that was like, define the structure the exact same way I did for ODP
Mm-hmm.
2, and then return 0, and that was the whole function. And it's like, no, you can't do that.
Interesting.
So, but if I changed it from an integer to just no return value, commented out the return value, it was like, that's good job.
So if it's void, you can't have a return value.
Yeah, so I just commented out return value.
Okay.
And changed it from an integer function to a void function. And then I was like, now there's no problems.
But you had an integer function and it wouldn't let you return.
Or when I put an integer function, the compiler error said that like something was going wrong in between defining the structure and the integer. It wanted me to name, if I named the structure, it fixed it.
Okay. Yeah, can you show me right after class?
Yeah.
Because that sounds intriguing. And it may be one of these things where the error message the compiler was giving you was not actually useful. Sometimes it thinks the problem's here, but it's actually something unrelated, but it can't tell. But yeah, if you can show me, we can take a look at it. All right, so good on those first ODPs. So 204, which is due tomorrow morning. So here we're starting to work with this array of struct nodes as a linked list. And there's a lot of wordage here, but the synopsis is pretty simple. You're making a function called getFirst. It takes the struct node array, and it takes a pointer to an integer, which we call error. We use this to send back a piece of information to the caller. Okay, and we also return a function value. So C, we have to return things by passing the address of a variable, just like scanf. We wanted to return a value to a variable, so we pass the address. So you're making this getFirst function, and here's what it does. It looks at the sentinel node that's stored in index 0, and it says, is this pointing to a node? So you look at the next field and see if it's equal to myNull. If it's equal to myNull, it means there's no data node in the linked list. So the list is empty, the function should return 0, and error should be set to 1. So in your code you'd say star error equals 1, right? That sets a value for a variable that was passed to you, and then you should just return a 0. So that's if element 0's next field is equal to myNull. Otherwise, element 0's next field is not equal to myNull. It's the index of the first node in the list. So go to that index entry, grab the data field, return that as the function value, and set error equal to 0. So let's do a picture. And I don't think we're doing anything with the valid flag in here. So we don't care what's in the data field of the sentinel node. If this is myNull, set error equal to 1 and return a 0. If this is anything other than -1, let's say this is equal to 3, that's saying the first data node is right here at index 3. So in this case, set error equal to 0, and you would return 25. So in view of a linked list, This is a function which can be used to tell you what the first data node in your linked list is. In this case, we've got a list that looks like this. And that's the first node, so this function returns a 25. And if the list is empty, it returns a 0, but we know that that's not a data value of 0 because we can look at the error variable and say, oh, error is equal to 1, the list was empty. Does that make sense? And the code is probably about a quarter the length of the assignment, right, in terms of lines of code. It's probably like 4 or 5 lines of C, actually, to do this function. So all the rest is boilerplate, right? Testbed is main 204, compile it up, assess it, and if it's not working, write a test program and go in with GEB and see what's going on.
Is this how someone would actually sort something in like the real computer science, I guess, world?
Did
or
you
do they have more sophisticated ways of doing it?
For sorting?
Yeah.
You could sort like this by throwing things into a linked list. It's not really efficient, right? To sort n things that way would be n squared, which is kind of bubble sort efficiency. Plus, this is more complicated. But there are cases where you're going to be pulling stuff in and you want to keep them in order in a list, and so you would be, doing this to sort them as they come in. But usually because you not just want them sorted, but you also want them in this structure so you can do quick inserts and deletes. And yeah, this is real data structure stuff. Right, I can't tell you how many linked lists I've coded in my life or used in my life. It's a lot. And our linked lists right now, we have a little integer stored in here, but that could be anything other than an integer. It could be a character. It could be an array of characters.
It could be like our dictionary.
It could be a dictionary. It could be a linked list. You can have a linked list of linked lists. In fact, you will in one of your PAs. Right? So we can take arbitrary data structures and build linked lists out of them. And when we learn about trees, we can make trees where each node is a linked list. And the nodes of that linked list might be other trees, and it can get really, really big and hairy and complex. And you will laugh at these someday because they'll be trivial for you to do, because you understand the concepts that thoroughly. All right, so any other questions on 204? Make sure your function's returning the data value of the first node, not the next value of the first node. All right, so I think in the instructions it just says if there is a first data node, your function should return that value. I mean the data value, right? The number that's stored in the list. All right, I wanted to make a comment on Putty. I wanted to do this in 224 and I never got around to it. Most people, if you're running Windows, you're using Putty. This is a pretty tiny font, but you can do things with your Putty configuration to make your life a little better. So you can put your name and IP address up here. So I've got nick@linuxengrcs.com. And under Window, you can set how many rows and columns you want if you want a bigger window by default. Right, I can change that to whatever. I can make this 120 by 36. You can set your lines of scroll back. Normally it's like 2,000 or something like that. Make it big enough that you can be here programming for hour after hour and you can still go back and see what you did. So that when you're getting some weird result, like I thought I did this before, but it didn't give me 10 out of 10 and now it is, you can actually go back and see exactly what you did. And when I keep telling you to like copy and paste things, you want a big memory.
For the person you showed us, would that just be like our username?
Yeah, so first initial last name at linuxengrcs.com. Appearance, you can change your font. So I've got mine set to a font called Free Mono, and I've got it set to 16. Courier, any kind of mono-spaced font, right? Proportional spacing doesn't really work well with coding because things don't line up. But Courier is a pretty standard proportional or fixed space font. Courier New is available. And make your font size, whatever you like. I'll make it 18 just for emphasis. You can make it bold if you want. And you can set your colors. So I like a green font with a black background, or maybe an orange font with a black background, but you can set your colors however you like. And when you're done setting all of this up, go back to Session, and under Save Session, say Default Settings, and click Save. Okay, so let me cancel out of here. So next time I run Putty, all I got to do is hit an Enter key. It brings up my login. It didn't say my font size. It brings up my login, and all I got to do is put in my password. And I'm logged in and I'm ready to go. Right? And it's one of those things where every time you go into Putty, you got to type everything in. You got to remember the server name. You got to change your setups if you like, and so on and so forth. Put those into your configuration, right? And start thinking in general when you're doing things in a Unix environment. That's kind of the name of the game. You can customize the heck out of everything. So if you find yourself always doing the same 10 minutes worth of stuff throughout your coding sessions, put it in a script, right? Put it in your bash RC. Do something to set things up the way you like. You should never have to deal with some random decision that some designer somewhere made 5 years ago that's making your life painful when you have to use some utility or do something. If you don't like VI, find a different editor. If you don't like any editors that are out there, write an editor. It's not that hard to do, actually. It's just a file manipulator. Make your own editor. Could be the thing that we're teaching in 224, like 10 years from now. All right, so I just wanted to mention that as a kind of a general notion. So linked lists, and we're going to stick to Sentinel nodes from here on out. So I'm going to start with a Sentinel. And we'll use our usual list. And again, if we're implementing this linked list with our array of struct nodes, header is just an integer that's equal to 0, the location of the Sentinel node. When we're actually putting these things in memory, header would be the address of the Sentinel node in memory. But for now, header is just a variable equal to 0. And so let's do something like, let's look at delete. So we want to delete the number n, some integer, from our list. And I'm going to assume that we've already checked and made sure that n is in the list. So we don't have to worry about running out of nodes. So before you do your delete, call your search function. If the number is not in your list, don't do anything. So we know that we want to delete, say, the number 20. And we know it's in the list. Remember, the idea is we can start moving through the list. We can look at each node's data value. When we get to a node that's 20, we know this is the node we want to delete. But we need to adjust the previous node. We've got to somehow back up to this 10 and say, okay, take the 10, and instead of pointing to 20, point wherever 20 points. Point to this node's next value. So if we just move through and say, is this 20, is this 20, is this 20, when we find 20, we've lost a piece of information. So this is why we have this idea of like previous and current, a pair of pointers. So we're going to start off with previous being the Sentinel node, and current being the first actual data node. And we're going to check to see if current is equal to n. And if it's not, then we're going to move these forward. and see if current's data node is equal to n, and in this case it is, yes.
Wouldn't we also have to know the next node, or could we just use that?
We can use the .next field. Yeah, exactly. So we move ahead, we check current's data value of 20, that is equal to n. And so we know that we want to delete current. And we have all the information set up that we need. All we need to do is take previous and change its next to be whatever current's next is. So now this is going to change to point to there, and we're done. So if you have that picture in mind and that modification to the picture in mind, the code kind of writes itself. So previous equals header, and current equals header.next. And then if current.data is equal to n, then we want to delete the current node. Otherwise, what do we do? Move down the list. So we change current to be current.next, and we change previous to be previous.next. And then we're going to go back and we're going to search again. So it's really a 3-instruction loop. Check to see if the current node's data is the thing that we're trying to delete, and if it's not, change current to be the node after current, change previous to be the node after previous. We could also have just said previous equals current if we want. And so this marches down the list, previous current, previous current, previous current, until this is the node we want to delete. When we want to delete current, what do? Take the previous node, and instead of pointing to the current node, point to whatever the current node is pointing to. So take the previous node, and instead of pointing to 20, point to what 20 pointed to, which is 30. So now our list skips over the current node, and we've basically removed it from the list. And once we delete a node from the list, we need to somehow free up the memory that was being used for that node. So you're going to write a function release node that's going to go through and basically set the valid flag to 0. So that the memory that was being used to store this 20 is now available to store something else. And then in this case, we can just return. Because we're done. We did our delete. We don't have to loop anymore. So that's pretty comprehensive pseudocode for a delete function. Yeah?
Why wouldn't you just set the valid to 0 when you delete it? That's part of the same process.
Yeah, that's what you do in this comment.
Oh, okay. Sorry.
But in your programming assignment, I'm going to ask you to call that release node function to set the valid flag to 0. Yeah?
For PA1, do we assume that the size of linked lists are always going to be unfilled?
Yes.
Okay.
But it doesn't hurt to set up a defined variable and use that everywhere. So that if you want to use this somewhere where your linked list is 1,000, you can just change one thing in an include file, and now you got a general purpose package. Yeah?
Could you review header files?
Yeah, I was just thinking while I was saying that I probably should. Does this make sense so far? Okay, let's look at header files. right, there's some great code. Don't ever turn that in for your final submission. I think this will compile though. Yay. All right, so you've got something like this. You've got an array of struct nodes instead of integers, right? And it's 100. And in your print routine, you go through all 100 entries and you print them, or you look for a valid or something like that. And this 100 is a magic number, right? So one way to get rid of that is to use a define statement. So I'm defining a symbol I'm calling list size, and I'm saying that symbol is equal to 100. This is something that's used before we actually compile any C code. There's a step of GCC called the preprocessor, and before any code's actually compiled, the preprocessor goes through and it finds all these statements that begin with a number sign. And it sees this statement and says, okay, anywhere I see the word list size, if it's not in quotes, I'm going to replace it with 100. And it lets you do the following. If you don't make typos. It lets you replace that magic number 100 with this symbol list size. So this is great because now if I want an array that's 10,000, all I got to do is change that one thing where I define list size to be 10,000 instead of 100. And when I compile, LL will be an array of 10,000 entries, and my for loop will go through 10,000 times and so on and so forth. But if your program is broken into multiple files, I need to put this define at the top of each file, because defines are only valid within this particular file. And so now if I want to change this back to 100, I've got to go through every file where I have this number sign define and change this to 100. And if I change it to 100 in one file and I forget to change it to 100 in a different file, bad things are going to happen. So I'd like to put this define statement in one file and include that file everywhere that I need to use this. So I'll make a file called main.h, which contains this single statement, just sets up the define. And then in here, instead of saying define, I'm going to say include main.h. And I put it in quotes to say this is coming from my current directory. Angle brackets say it comes from a system directory. Okay, so here's the action. I start to run GCC. Before it compiles anything, it looks at this number sign and include. It says, okay, I need to find main.h. What's inside there? There's one line. It says define list size 10,000. So it replaces this number sign include with that line. Define list size 10,000. And now anywhere it sees list size, it uses 10,000.
Can we put our structure definition in there?
Really good thing to do, yes. So put your structure definition in a .h file, and every file that you use it in, if you include that, it'll pull in that code. And it's a way to avoid typing the same thing over and over and over again. And that's really useful with structures, because structure is one file. You might put the things in a different order, and you'll never get a compiler message telling you that happened. You'll just get really weird results when you run your code, and it'll drive you crazy. So this will sort of save you from mistakes like that. And if you decide, I really need something else in this structure, so you want to modify it, you only got to modify it in one place. Just go into your .h file and change it there. And there's nothing magic about .h. It's just a convention. Files that are going to be included, we put in a .h. Files that actually have executable code in them, or C code that's going to be compiled, we put in a .c. All right, so delete makes sense. So let's do the same thing for insert. And like I say, delete, we can assume that the number is in the list. We can search for it first, so we know that we're going to eventually find where current data equals n. if the number's not in the list, right, we need to make this while loop conditional, and basically, if current ends up being null, right, if we were down here, previous and current, and we didn't want to delete the 30, and so we set previous to 30, current will end up being equal to null, because that's what 30 points to. That's when we know that we've hit the end of the list. And at that point, we could exit out and say there's no such number n in the list. But the easier way is just call your search first.
Having the Sentinel node doesn't mean that our array would have to be 101.
It means we can only store 99 data values in our array, right? In our linked list. Because index 0 is always a sentinel. So yeah, the number of nodes is actually one more than the number of pieces of data we have. All right, so let's insert 25, or n in general. And same drill as before, we're going to have, I'm going to make you a clean list. Because I want to update the arrows. So here's our sentinel. There's our 10. There's our 20. There's our 30, and there's our null. Okay, same drill as before. We're going to have a notion of previous and current, previous and current, previous and current. And as soon as our current node is bigger than n, we know we want to insert right before that. So yesterday I called this before and after. Today I'll call it previous and current. So start off with previous at the header, current at the thing that previous points to. And we want to see if current data is bigger than n. And eventually, we'll get down to this situation where current data is bigger than n. So how can we code this? Current equals header. Sorry, previous equals header. Current equals whatever previous points to. And then if current data is bigger than n, insert before current. Otherwise, again, just move down the list. So current equals current.next. Previous equals previous.next. And then go back up to the top of our loop. So this moves us down. In this case, if we're inserting 25, we're going to fire this if statement when we're in this situation. Previous is 20, current is 30. So what do we do here? We have to create a new node. We have to find a spot in our array, for example, where we have a new node. So we're just going to call our getNode function. And it's going to give us an index in the array that's available because the valid flag was 0. And our actual getNode in PA1 is going to set the valid flag to 1. Okay, so we've got a new node. We're calling it temp. And we want to set its data value to n. So that'll put a 25 there. And then 2 adjustments to make. Bless you. Previous needs to point to temp. Temp needs to point to current. So previous next equals temp. So that does this. And temp next equals current. That does this. And you're done. So exit out of your loop at that point. You've done your insert, you're finished. All right, so what are we missing from here? What happens when you reach the end? Because this loop may eventually go off the end of the list. Right, so suppose we want to insert 50. Well, we'll march through previous current, previous current, previous current. Current's data is 30, that's not bigger than 50. So we're going to move forward, and previous will be equal to this, and current will be whatever previous was pointing to, which is null. And now if we try to check the data value in this null, we're going to get an error. Because when we say current equals null, that's not a node. It's saying that there was no node after this one. So current.data doesn't make sense. So we really need to have a check here. So loop back until current equals null. So if current equals null, we've gone off the end of the list. What should we do? Where should we put our new node 50? Current is null though, but yeah, that's the right spirit of it. But there's an alternative answer. So here's our list, 10, 20, 25, 30. So physically, where do we want the 50 to go? We want it to go after 30, right? And 30 is our node called previous. So in this case, we want to add to end. So temp equals new node. Temp data equals n. So here's our new node. There's a 50, there's temp. And then one line of code. How do we get previous to point to temp? Perfect. Previous dot next equals temp. So that says take the next field of this node, and instead of having it be equal to null, have it point to temp. And then, unless you do this in your get node, which you might, temp.next should be null, or my null. So this is null. And what's our list look like now? Sentinel points to 10, 20, 25, 30, 50, end of list.
What happens to temp then?
What happens to temp?
Yeah,
It's temporary. The node is still there. Temp was just a temporary variable. It was local to our insert function. So this at some point is going to start feeling a little weird, because we're going to be doing the same things in code over and over again when we're looping through. We're doing the same things, but these variables, previous and current, are somehow pointing to different pieces of our linked list. And temp is pointing to a new piece of our linked list, and then we join it into our linked list by adjusting this thing. And the variable temp is temporary. It can go away. We can change its value. But the connection from this node to this node is permanent, right? Because in this node, the 30, we have this field in the struct node called next that we've set equal to whatever location we store this 50 node in. And if it doesn't feel a little weird now, it'll feel weird when we start doing this in memory. Because we're going to have local variables that we're going to use and overwrite and then forget about, but our data structure is going to persist because it's actually stored in memory somewhere. For now, it's stored inside this array of struct nodes, so it persists.
So when you malloc something to a temporary address, it is still there even though you're not
It's still there even if you're not pointing to it anymore. If you change the thing that was pointing to it, it's still in memory. As long as something points to it, like, you know, a previous node, it's still there. Yeah. So all of this I would code up as probably a while loop, while current is not equal to null. And that's going to seamlessly take care of the edge case where you start off with an empty list. And you're always going to start with that edge case because your initial list after you call initialize is empty. So let's just look at that one edge. So our header is 0, points to the sentinel. It's got some unknown data value. And the sentinel's next field is null. So this is an empty list. And let's go ahead and insert a 50 into our empty list. So we're going to set previous equal to header. Which for us is index 0. And we're going to set current equal to previous dot next. Well, previous is the header, the next field is equal to null, so current is equal to null. And now we're going to go into our while loop while current is not equal to null. Well, current is null, so first time through we're going to kick out of this while loop right away, and we're just going to come down here and do this. And this is going to make a new node called temp. It's going to set the data field equal to 50. It's going to set previous, which is headers next, to point to temp. And it's going to set temp next to null. And there's our list with a single node we just inserted, which was 50. So this works fine with an empty list. It'll work similarly fine if we're inserting something before the 50. And you can run through that on your own. And we already saw it works fine if you're inserting at the end of the list. And it works if you're inserting in the middle. So all the potential edge cases seem to work fine. All right, so that's an insert and delete. Search is a subset of that, right? Search, you're doing searches in here, so you can just code that up as a search and return found or not found. And we did traverse yesterday.
Is header just an integer?
Header is just an integer in this case, and in fact, it's always going to be 0 because that's where the sentinel is. All right, so you've got enough to do PA1 at this point, modulo, you know, trying to figure out what I'm talking about. So, all right, cool. Have a good weekend if I don't see you in 2:15. Have a good weekend anyway.